Okay, pre-calculus students, we are going to do some modeling with functions. So if we look at right over here, modeling with functions, we are going to take some of the problems, especially regarding quadratics, and we are going to do some, somewhat difficult solutions. So it says a farmer is making a pen out of 600 yards of fence. He will be dividing the pen into 3 sections that are all equal in size. What dimension should he make the pen to maximize the area? So, we got a farmer. He's going to make his pen. He's going to divide it into 3 sections. They're all the same size. He's got a total of 660 yards of fence. So, and we want to be able to figure out the maximum area. Well, we have this width and we have this length. And you can see that we have a width there, we have a width here, we have a width here. If I add up all those pieces, I get my 660 yards. So width plus width plus width plus width plus 2L plus length is equal to 600. Or 4W plus 2L is equal to 600. We also know this. We're trying to find the area. We know that area is equal to length times width. So what we can do is we can solve for one of these pieces. If I subtract 4W from both sides, I get 2L is equal to 600 minus 4W. Divide both sides by 2. L is equal to 300 minus 2W. I'm going to substitute that in. So I have the area is equal to 300 minus 2W times W. What you notice is that if I distribute that W through, I have the area is equal to W. I'm sorry, I'm going to write this as negative 2 W squared plus 300 W. And if you think about it, that's a parabola. It's a parabola that goes down. And we have what is referred to as a maximum value. And that happens at the vertex. How do we find the vertex of something like this? Negative b divided by 2a. Negative 300 divided by negative 4 is 75. So 75 is the location. What does the question ask? What dimension should he make the pen in order to maximize the area? So 75 is actually the width. That's what we've solved for. We've solved for W. This point up here would be the area. So we could plug it in to get the area. But 75 is where the maximum happens. That's the width. I can use that to figure out the length by plugging it into my equation right here. Four times 75 plus 2L is equal to 300. I'm sorry, 600. So I have 150. Oh, I'm sorry, 300. Excuse me. 300 plus 2L is equal to 600. So 2L is equal to 300. So L is equal to 150. So there we have it, 75 by 150. That's what we got. So we've been able to solve this problem by, again, finding a maximum, and there you go. We got a couple others that we'd like to try. Look at next side. This time, farmer is going to build a fence against the barn. So he's got a barn. He's going to build his fence. He's got a width and length. He's got 320 feet of fencing. So if you add up the widths and the length, you get to be 320. And again, we want to maximize the area and find the dimensions. So area is equal to length times width. Solve for L, we get L is equal to 320 minus 2L, or 2W, excuse me. Take that 320 minus 2W, plug it in for L. So the area is equal to W times 320 minus 2W, where the area equals negative 2W squared plus 320W. Again, if you were to graph that, the shape is a parabola. It goes down. We're looking for the vertex. That's where the maximum happens. So we do negative b divided by 2a. So we have negative 320 divided by negative 4. We get 80. So again, 80 is the location. If we plugged it into the area function, we'd actually get the area. So 80 is going to be my width, which I've solved for. And in order to figure out the other part, I plug it back in. So 2 times 80 plus L is equal to 320. 160 plus L equal to 320. So L is 160. So 80 by 160 is going to be my result. So again, the question was, what dimensions should he make? You should make it 80 by 160. And one more. A box with an open top is to be constructed to form a rectangular piece of cardboard with dimensions 10 by 18 by cutting a square from each corner and folding the sides up. Find the largest volume that the box can have. And we cut corners out. I know that volume is equal to length times width times height. Well, the length of my box right now is 18, but I'm going to cut x off of each end. So my length will be 18 minus 2x. Similarly, when I cut x off of those sides, it will be 10 minus 2x. And when I fold the sides up, I'm going to have a height of x. So my length, 18 minus 2x. Width, 10 minus 2x. Height, x. That means the volume is, got to multiply these out. Negative 2x times negative 2x is, of my x in front, 4x squared. Negative 2x times 10, negative 20x. 18 times negative 2x, negative 36x. And what else? 18 times 10 is 180. So my volume is equal to 4x to the third minus 20x, well, I'm sorry, 20x and negative 36x, negative 56x. So minus 56x squared plus 180x. And if we graph this, it's not a, it's not a parabola. This is a cubic. But we talked about finding local maximum. We're looking for that spot. And in calculus, we can solve this, but we can't solve it in pre-calc right now. We have to be able to use our graphing calculators to help us. So I'm going to take out my graphing calculator. I'm going to type in my function. Oh, doesn't want to turn on. Let me pause the video. Okay, there it's on. Let's see if this works. Okay, going to y equals. And we got 4x to the third minus 56x squared plus 180x. And if you think about this problem, we want to find where it's happening. So we want to find an x value. So if you think of, the biggest square that you cut off here would be 5, because 5 and 5 is 10, so you'd have the whole side cut off. Over here, the biggest you could cut off is 9. So you can tell that 5 is really the biggest square that you could cut off, 5 by 5. So I should be able to, see it as long as I have a x maximum value of, 6 should be fine. I'll just go up to 10 just for good measure. But y values, who knows? Who knows right now? Let's graph this thing and see if we can actually get an idea for what's happening. Oh, I see a line. I see it go back up. Okay. So if we compare that graph to what I drew in the red, you can see that we maybe need to look at that. Maybe need to go a little bit higher. So, how high do we go? Well, what volume could we have? Let's just suppose we had a 10 by 10 by 10 box. Well, 10 by 10 by 10 is 1,000. That's not possible for an option to have a 10 by 10 by 10, but that at least gives us an idea of, what we should plug in. So we'll try 1,000. I want to make my scales 100 so I don't have so many. If I graph it now, okay, I can actually see the top. So if you don't like how tall that is or how high you go up, then we could reduce it, make my window maybe down around like 300. And then I'll go down to negative 100 so this looks a little bit better. So you got to know kind of how to use a calculator and work around. So there's my graph. There, that looks a lot better. So I'm looking for that spot, that maximum. And the way that we find a maximum is we do our second calculate. We go to this spot, and we actually go down and find our maximum. We practice this on your sheet. Press enter on maximum. I need to go to the left side of the max and press enter. I go to the right side of the max, press enter, and press enter again. Now you're going to get two values. The x value is 2.06. That is what size square you cut out. The y value is actually the volume. Since we wrote an equation for volume, y is the volume. So 2.06 and 168. So I'm going to write that down. 2.06, 168. That's the location of my maximum. Let's answer the question. The question says, find the largest volume that the box can have. Well, I want to know the largest volume. I'm not really concerned about the 2.06. That's just the x value. Volume, largest volume is going to be 168. And were we cutting out inches here? Yeah, inches. So volume is a cubic measurement, so inches cubed. There you go. There's an introduction to modeling functions, modeling problems with functions and solving them. So good luck. Hope you do well.